Hello guys, it's the Caribbean Bookworm and welcome to part 4 of our journey to relativity. In the last video, we basically looked at these various applications of the new symbol that we call the Levi-Civita symbol, which showed basically some properties of totally anti-symmetric, objects. And at the end of the video, we started introducing this concept of taking the curl of a vector field, etc., etc. And we mentioned by the end of the video that in this video, in part 4, we're going to be mainly looking at vectors in curvilinear coordinates. And to be more specific with that, curvilinear coordinates basically imply a coordinate system in which basically the axes which you have, at least for, say, your basis vectors, they're curved, basically. They're not basically these smooth, rigid planes, such as you're used to in, say, a Euclidean geometric system. So if you want to look at that, one thing which can immediately give you a little bit of a hint as to what we want to pay our focus on is the concept of the basis vectors. Now, earlier, when we looked at the basis vectors in the various 3 videos, we denoted, for example, in Cartesian coordinate systems that we had the following basis vectors. We had E2 hat, E1 hat, and E3 hat. Each of these basis vectors basically in Cartesian coordinate systems relating to one of the directions in which something can change in a given coordinate system. So something can change with the direction of the x-axis, the y-axis, or the z-axis. Now, another interesting property which we mentioned about these beforehand in, I think, Journey to Relativity Part 2 is that these basis vectors, they have a magnitude of 1. And basically what that would imply is that basically the length of any one of these basis vectors would be equal to the number 1. And that is because basically we said that these basis vectors, at least in Cartesian coordinate system, they were also unit vectors. And unit vectors, this unity property, is what's basically telling us that these vectors have a magnitude of 1. But very interestingly, basis vectors do not necessarily have to be unit vectors. You can have non-unit basis vectors as well. And that is actually what we're going to be looking a lot at today. Say we were looking at a coordinate system which we looked at earlier in part 1 of our journey to relativity, and that is basically the cylindrical polar coordinates. So in essence, a cylindrical coordinate system, but we're mainly looking at the xy plane. So with that, we would have the y-axis, let that be x2, the x-axis, let that be x1, and we have a radius, basically a radius of the cylinder in which something is practically rotating, you could say, and we called that rho. The angle made basically by the this radius right here, and the x-axis, we call that phi. And very interestingly, the base vectors which we can use to describe the Cartesian coordinate system, we can also use those to derive some basis vectors that we want to describe things in this cylindrical polar coordinate system. In essence, if we have a point on the cylinder right here, we can describe it how it is growing with respect to phi, and how it's growing with respect to rho, basically. This is how we talked about these basis vectors, as basically they should describe the direction in which things are changing in your given coordinate system. In this case, things can change with respect to phi, the angle right here, and that basically means that it can change tangential to this given line right here. So it creates an angle of 90 degrees right here, and you can get a basis vector that looks like this, which we will call v phi to indicate that it is the basis vectors which shows the change with respect to phi right here. We can also show the change if, say, we change the distance from the origin to the point on the cylinder. So in essence, if we change the radius of the cylinder, that is what we will indicate with the basis vector v rho right here. So you can think of these two basis vectors as being orthogonal to each other because one basically changes 90 degrees from the radius of the cylinder, and this one changes literally parallel with the cylinder. So for that reason, you know already that if I take, for example, the dot product of these two basis vectors, then what I would get is 0 because the angles between them are 90 degrees. And if you remember again, if you take the dot product, you have the magnitudes of them times the cosine of the angle. Cosine of 90 degrees is 0. So the dot product would in essence be 0. Now, very interestingly, you can describe these two basis factors as, in essence, you can describe them in terms of the basis factors of the Cartesian coordinate system as well. That is very much possible, and for that, we would need to draw the basis factors for the Cartesian coordinate system as well. In your mind, you can think of this as taking the basis factors for the Cartesian coordinate and just move them right here to this given point. There is nothing wrong with that, and we can see why this is handy in just a moment. Say that we have now our basis factors in terms of the Cartesian coordinate system, so this would be E2 hat, since it would in essence be y hat, the basis factors in terms of the y direction, and this would be E1 hat, the basis factors in terms of the x direction, so x hat. Now, what we can immediately notice is that the angle between E1 hat and V rho hat, it should, by just geometry, be the same angle as the angle right here between x1 and rho. So in essence, we know that the angle between this will be equal to phi. If I can draw it well, it looks something like that. Now, one other thing that we'd be interested in is what is the angle right here, the angle between E2 hat and V phi hat. Well, the answer to that is that the angle is phi as well. And we can see why. We can just derive that very quickly. Say if we call this angle our mysterious angle that we don't know, so a question mark angle. If we have our question mark of an angle right here, we can't find it. Let's look at what we have. We have another 90 degrees right here because E2 hat and E1 hat are also orthogonal to each other. And we know that if we have 90 degrees right here and 90 degrees between the two base factors which we're describing for our cylindrical coordinate system, so V phi hat and V rho hat, then basically our answer for this question mark should be 90 degrees minus whatever the angle between E2 hat and V rho hat is. So what would this angle be in essence? This angle would in essence be just 90 degrees minus phi. So in essence, we would have for our answer that the question mark should be equal to 90 degrees minus, in this case, 90 degrees again, but minus phi. Minus phi. Now, if you work things outside of the bracket, what we will see is we have 90 degrees minus 90 degrees, and that's just 0. And then we have the -1 times negative phi, which would just be plus phi, showing in essence that our mysterious angle right here should also be phi, similar to the one that we have right there. So with these angles in mind, now we can actually write our V phi hat and V rho hat in terms of the basis factors for Cartesian coordinate system. So for example, V rho hat, if we use a little bit of trigonometry, we can see right here that it should be, well, this component right here, which should be V rho hat multiplied by cosine of phi plus this vertical component right here, which should be V rho hat again, multiplied by this time sine of phi. And now in essence, one thing which I forgot, of course, is to multiply it by their respective base factors. So this component right here, this horizontal one, multiplied by the base factor E1 hat, and this component right here, multiplied by the vertical component E2 hat. Now we can do the same thing, but for V phi, and for V phi, what we will get is the basically this component right here, which is what we would call in this case, say, the horizontal component of this vector. This should be equal to basically V phi hat multiplied, in this case, if you can look at it in terms of a triangle, it will be multiplied by cosine of phi. And then of course multiplied by its respective base vector. And now we have a situation right here. We can find the vertical component, you could say, of v phi hat. The only thing is, because it will be pointing in this direction, which is opposite to what we've chosen to be by convention our positive direction, we would have to add a negative sign to this. So we would say that in essence, what we would get right here is negative of v phi hat, multiply this time by the sine of phi, and then of course multiply by its respective base vectors, which would be e1 hat. So in essence, we have described our v rho and v phi hat in terms of Cartesian coordinate systems, because you can think of e1 and e2 as being x hat and y hat. If you want to even check for their orthogonality without using the geometric argument that they are 90 degrees from each other, because this one moves in this direction and this one in this direction, so they should be 90 degrees from each other, you can literally still see that they're orthogonal by taking the dot product of them. And what you will get is an answer of 0, which would imply again that these are orthogonal to each other. This is something that you will get because you have cosines and sines in here, which will boil down to eventually cosine squared of phi plus sine squared of phi, that would be 1. And then eventually, if you continue to work things out, you will see that, okay, you would have an answer of 0 consistently, which would be why they're orthogonal. Now that we have that, we can think of the simple fact that actually we can describe any vector right now in terms of these cylindrical coordinates instead of the Cartesian coordinate system. So for example, if I have a vector v right here, in essence, I can decompose it in terms of v rho hat and v phi hat. And basically the components of this vector v right here, if I were to project a line right here and right here, I would have a component of the vector v of v rho and v phi, basically. So the upper index right here indicating which term you're working with. So in essence, if we were to describe this vector v right here, but in terms of the basis vectors used in the cylindrical polar coordinate system, then we would say that the vector v should be v rho multiplied by the base vector v rho hat plus v phi multiplied by the base vector v phi hat. So very similar to Cartesian coordinate system, you have your vector that consists out of the components with respect to the given base vectors that you're working with. Now, looking a bit more closely at this, we see that the v phi hat and the v rho hat, these are also unit vectors. These are also magnitudes of 1. So what about the thing which I said earlier, that you can have base vectors which are non-unit, basically, that are not 1? Well, because in physics, for example, we use a lot of unit vectors, we can typically say that these unit vectors are called, in essence, physical bases. So physical bases or bases, they're basically unit vectors of any arbitrary index, you could say, which have a magnitude of 1, and generalized basis vectors, which we will denote with the letter G. These general basis vectors are, in essence, they can have a non-1, basically, magnitude. Those are what we will call the natural basis. So natural basis we will denote with the letter G. And in essence, well, with any index, I, in essence, the way in which we can find a physical basis, so a basis with a magnitude of 1, from natural bases, which are these more generalized, you could say, bases which can have any magnitude, you could say, is by the following. We could say that the physical basis right here, so phi I hat, could be E1, E2, etc., it would be equal to the natural basis chi I hat divided by its magnitude. Because we can remember that the magnitude, again, it can be something that is not 1. So if we do this little process right here, it should in essence spit out your basis, your physical basis. And in essence, if you want to find the magnitude of the natural basis, so for g I hat. The way in which you can find its magnitude is by just taking the dot product of gi with itself and doing the square root of that. So you have the square root of gi hat dot gi hat. This would in essence spit out the magnitude of the gi hat, so of the natural basis. As we saw earlier, and in, for example, part 1 of the Journey to Relativity, the manner in which we could express the Cartesian, components of a different coordinate system was by looking at things geometrically and looking, for example, at trigonometric things that we need to pay attention to, such as, for example, in the spherical coordinate system, or just as we saw with the cylindrical polar coordinates. We had to look at angles, we had to look at radius and distances from origins and such. Is there a way in which we don't have to rely on basically just pure visual geometry and just using analytical techniques to still derive basically basically the Cartesian components of a given coordinate system? And yes, there is a way to do it analytically. The way we would do that is by looking at something which we introduced earlier in part 2 of our Journey to Relativity, and that is the displacement factor. So if you remember, if you have, say, a random object on a curve, let's say a surfer going down a wave, then the way in which you can think at how this object or this surfer is displacing from the wave is basically very much the line which you would draw, which would just basically scratch this slope this incline right here, and that would be the displacement factor. The displacement factor, if I were to draw it in physics, I would draw an arrow to give an emphasis that it is a vector. How do we go about finding basically the actual value for this displacement factor? Now that has to do with the fact that we need to take the derivative of the position factor. And we describe the position factor as r x I e I hat. If you remember in our previous in our first video about factors. So this xi, of course, represents basically whatever you have for your x1, x2, x3, etc. And your ei represents, of course, your basis. In this case, because Cartesian, it represents your physical basis for the position vector. Now, how I go about finding the derivative of this means that we need to, of course, find the derivative of xi e I hat. And if we are to do this, we see that we have two things right here. So in essence, we would have to use the product rule. So we would first get the derivative of the xi multiplied by the normal ei hat. So dxi multiplied by ei hat, plus this time the derivative of ei hat times just the normal value of xi. So xi multiplied by di hat. But because we said that in Cartesian coordinate systems, these basis factors are constant, they don't change, they're not parameterized, we can in essence notice that then the derivative of a constant is 0. So this whole term right here falls out, leaving us with this value for our basically our displacement factor. Now, it is not always that the derivative of a basis factor is 0. Sometimes you can have your basis factor be a non-constant variable component, and in that case, you do need to, for example, use the product rule in such a case. So keep that in mind. Now that we have our directional derivative right here, something that we can do is we can find the magnitude of the directional derivative, because that will in essence give us basically the small increment which this, for example, in this story, the surfer, but in general, it will give us the magnitude of the displacement of this object given this basically direction. In essence, what you would do then is, if I want the magnitude of the displacement factor, then of course I'd want the dot product of this with itself. What that would look like is the following. So I'd have to take the square root of dxi multiplied by xi hat. dot, and because we're doing the dot product, you remember that you do have to change the index, the dummy index of I. So we can call it any other thing that we want. Say the letter J, we can say that is dx j j hat, basically. And if, for example, we wanted to remove the square root right here for a reason which we will see why, then if we wanted to take the square root, we can just, if we want to remove the square root right here, you can just take the square of the magnitude of the displacement vector. That would, in essence, just remove the square root right here, leaving us with the dot product of dxi hat and dxj ej hat. Now, if we write this out in terms of index contraction, I will just remove a bit of the curve which I drew right here. If we draw this out, it would be basically the, and again, in terms of index contraction, it would be the components of these two vectors right here. So dxi multiplied by dxj, and then the multiple of this times the dot product of their given respective basis factors. So it will be ei hat dot ej hat. And you might have perhaps noticed a pattern already. This looks eerily similar to that which we've described in the first video, and that was the metric. Because you have these two things multiplied by each other times the dot product of the base factors, it literally looks like that which we call dl squared, which was the metric. And you'd be correct in that assumption. We can literally say that, for example, ei hat dot ej hat, you can literally say that that is the Kronecker delta of ij, and say that then the square of the displacement vector is equal to the metric in, say, given Cartesian coordinate system. But even though we're talking about Cartesian coordinate system, we can now generalize this to any actually coordinate system. And that's what we're going to do right now. In essence, the way in which we can define the metric, say, given in a coordinate system, is by basically describing it as the magnitude of the direction of the displacement vector. And that makes sense. We said that the metric was basically the infinitesimally small the displacement or distance that you can have in a given coordinate system. So it makes sense that from basically this, the metric basically just popped out of it. But now let's try doing this, but with natural basis instead of physical basis. So in order to do what we wanted to do, we remember that, for example, if in any coordinate system you have, for example, the x1, which is the Cartesian correspondent to that particular coordinate system. I'm going to draw it a little bit bigger, perhaps for a little bit more clarity. We said that, for example, in spherical coordinate system, that x1 was, if I'm not mistaken, x1 was equal to r sine theta cosine phi, and for example, x2 sine theta sine phi. x3 was equal to r cosine theta, basically. So in essence, what you can see here is that we describe each of the axes. So say xi, with say I being able to undertake the values of 1, 2, and 3. We describe them in terms of theta, phi, or if I am to be more specific, r, theta, and phi. So we were able to describe them in terms of these three values, basically. So if we were to call these, for example, if we were to call r u1, u2, and u3, we can say that our xi, in essence, depends on these three inputs. So with that in mind, we can take for any given coordinate system that, say, in our specific example, has just three inputs, but it can be as many inputs as we want. For our position factor, for example, we can take that r would be, say that it has three components, so three Cartesian components again. We can say that it has xi, u1, u2, u3, e1 hat, plus By the way, I'm calling this x1 as it's like the first, basically it's the e1 hat component of our position vector. But we have this plus x2. We have, in essence, these three components for our position factor. So we have this component right here, this component right here, this component right here, and what basically the things within the bracket indicate is that x1 depends on u1, u2, and u3, and so on for the others as well. So using a little bit of index notation, we can write this perhaps a little bit more compactly as xi, and within the brackets, a different index, j, e, I hat, in essence. So this right here would be our shorthand notation for the position factors. So if we wanted to find, in essence, the metric for this arbitrary coordinate system of u1, u2, and u3, we can, in essence, try and find, for firstly, the displacement factor, so dr, and then secondly, the magnitude of that displacement factor. So let's see if we can do that. Now, if we wanted to find the displacement factor for this, that means that we have to find the derivative of this term right here. So how we're going to do that is we say dr. Now, we have an xi that basically we put in uj. So we can put in, for example, one term, but it can be more terms. It can be u1, u2, u3, u4, etc. So by that logic, in essence, that means that we have to take a partial derivative and take the sum of these partial derivatives, because you can have more than one inputs in this case. So you have to every time take the derivative of xi with respect to these inputs. So that means that our first term right here, for example, when we're going to differentiate this, we're going to have to use the chain rule. So we're going to first find the derivative of this term right here with respect to uj. So del xi uj, but that is not over. So in essence, we found the derivative of this, but we also have to then multiply by the derivative of what's inside. And the derivative of what's inside, so the input, would then be duj. So it will be this value right here. And then because ei hat is a constant, we said that, for example, when we're talking about Cartesian coordinate systems, that this ei hat is a constant value and not a variable thing. So we don't have to use, because of that, the product rule. We will then just finally multiply by ei hat. Now this is an interesting expression because in essence we can start moving and swapping things around a little bit. For example, we can swap this duj for this ei hat, so we can in essence just write them in the other direction. What you would have then, if I do that, is you would have ei hat duj, and what I can also do from here on now is I can write this as the following. So I have my little partial derivative operator right here, and I can write my xi, and I would have, in essence, have to take the partial derivative that is very similar to just doing xi multiplied by ei hat. And then, of course, this bit right here multiplied by duj. The derivative, in essence, of what we had right here. This, interestingly, is what you knew to be the position vector, how we describe the position vector in the first place. In essence, we can write this a bit more shorthandedly as the partial derivative of the position vector multiplied by, in essence, the derivative of whatever our input was. And this, at the end, basically gives us an expression for the displacement factor in any given coordinate system, because we're taking things with respect to uj, and uj can be Cartesian, non-Cartesian, and any different coordinate system, depending on what you choose, of course, for u1, u2, u3, u4, etc. Now, a good portion of our task is done. Now what we need to do is basically find the metric, and we said and saw earlier that the metric is in essence the magnitude of the displacement factor. So if we were to do that, that means that if we want to find the metric, so this would be equal to taking the dot product of the displacement vector with itself. So that would mean that we have to swap the indices. So instead of j, we have to have something else. So we have our first bit right here. So partial derivative of r with respect to uj multiplied by duj dot. We have to basically now take the same thing right here and use a different index. So we have then, this should in essence give us the metric for any given arbitrary coordinate system. Now, to make a couple of very nice generalized notations and statements, we want to in essence look at the square of the metric. So we want to look at the square of the displacement vector's magnitude. So in essence, we want to remove the square root right here. So basically, if we have to take the dot products of these, that would mean that we would have to multiply these respective components with each other, and that all multiplied by their respective, say, unit factor. But in this case, we're not seeing any unit factor, and that is because this partial derivative bit right here is playing the role of the unit factor. It is giving you basically the displacement vector with respect to a given input. So it, in essence, plays the role of EI and EJ. But we're not going to write EI and EJ for following reasons that we're going to see pretty soon. But if you get the idea of that, that means that we can write this as duj multiplied by dui. Again, we're immediately using index contraction, and this all multiplied by the. So we in essence have right here, square of our metric is the following expression in which we have duj multiplied by dui, and it's index contracted, of course, and that multiplied by basically the dot product of these two basically partial derivative aspects with themselves. And this dot product right here, because it plays the same role as EI hat dot EJ had played earlier, we have a very specific name for them. Well, firstly, before giving you that specific name, we want to compactify this by stating the following fact, by stating that this, in essence, represents our natural basis. You were curious earlier as to what we would describe our natural basis to be. This would, in essence, be the natural basis of Gj hat, basically. So this is what that would look like. So it would look like Gj hat, and this, because it is with respect to the I index, it would give us the natural basis of Gi hat. So what we're describing right here, if you can write that a little bit more compactly, is the following. We're taking the dot product of Gj hat dot Gi hat. We're taking the dot product of the natural basis, because again, u1, u2, u3, etc. can be a non-Cartesian and a non-unit basis factor. So it doesn't have the unity property, so it doesn't have to be a natural basis. It can be a natural, or it doesn't have to be a physical basis. It can be a physical or a natural basis. So this is a more generalized sense of the metric. We define this dot product right here to be something called G with lower index ij, which stands for Gi hat dot Gj hat. And this is in essence something called the metric tensor. And the metric tensor is something which we'll definitely be looking more into, as it's even in the Einstein field equations, which is one of the main things that we want to get to in this series. But in essence, we're not gonna get there yet, and we're gonna be talking a little bit more about tensors in the following part of our journey to relativity. But in essence, what you need to know is that just basically we can express the square of the metric as this metric tensor right here multiplied by dui times duj, and where basically this Gij plays the role that the Kronecker delta, for example, played earlier. Now, if you remember in part 1, we mentioned that, for example, the whole technique of using scale vectors to, in essence, find your components for orthogonal coordinate systems Well, it only works for orthogonal coordinate systems, and we can actually very easily verify why with this new given abstraction. We can in essence do that by writing this new g factor in terms of a matrix. So let's try and do that. So say if we have a matrix right now of g, and we make it a square 3 by 3 matrix, since we're in essence interested in, let's say in this case, in 3D Cartesian coordinate system. We know that that is at least one of the many orthogonal coordinate system, but we're just going to be looking at a 3 by 3 square matrix. We can in essence, because we said that we have g, I, j, if these are orthogonal, then the only way in which I can have a non-zero value for this gij is by a very similar fashion as with the Kronecker delta. The only way we can have non-zero value is by having I equal j. So if I equals j, then you have a well, I can't write it right here, but looks a little bit bad, but non-zero value. But else, if I does not equal j, then you'd have a zero value for this right here. So if we were to keep that in mind and plug things in this 3 by 3 matrix, we can notice something quite interesting. We can take one glance at this matrix and notice immediately that a lot of these elements in this matrix will fall out because the indices are not the same. So for example, this G11, it's fine, but this G22 and G12 and G13, these will definitely be 0. This G21, that will be 0, and G23 will also be 0. This leaves us only with a diagonal that has non-zero values. Now, how we will see that these components right here will each be one of the scale factors squared is by the following. If you remember correctly, the scale factors were in essence, say if we have a scale factor hk and we have the square of that, would just be the partial derivative of, say, xi with respect to uk. Now, this is the square of a scale factor for, say, the variable of k. Now, what would we get if we have for our, say, our gij right here, if we have g11? Even a little bit more interesting, let's say that the k in this case equals 1. So you'd have x1 right here, or sorry, k1, k being 1 right here. All right, now let's see if we have this right here. We said that this gij represents the dot product of gi dot gj. And we also said that gi being a natural basis, this is equal to the partial derivative of the position vector by ui. Basically with the index right here, with the free index right here. And gj, the natural basis of basically the j component, that would be the partial derivative of the position factor with respect to uj. We recall that r equaled xi ei hat. Short interlude because I made a little bit of a mistake. When you're taking the partial derivative of r with respect to u1 and here, uj, you're still taking the ei and ej hat into account because even though I made the assumption that basically it is constant and non-changing, it is a necessary component when talking about the dot product right here. So I still have to write it in here. So you'd still have this multiplied by ei hat and this multiplied by ej hat, but we do still get basically ei hat being 1 and ej hat, the j also being 1. So if we write that in here, what we will get is we have the dot product right here of this dot this. So what we will get right here is we have the dot product of this dot this, and if we were to write this right here above, we would in essence have their components multiplied by each other, and every time multiplied basically by the dot product of the basis vectors. And because we do know one thing for a fact, and that is that the base vectors are supposed to be orthogonal in order to get a zero value, we know that if the base vectors here are the same, then we will get a value of 1, because we're looking at Cartesian coordinate system, so the magnitudes of these are 1. So if we do, again, our simple dot product, we will in essence get a value of 1 right here. So in that fashion, we can show basically that G11 is equal to just the square of the square of the scale factor of, say, the index equals 1. This is true for all of these other diagonal components. The only thing that changes is instead of the, say, for example, by width G to 2, that would give you the scale factor for H with lower index of 2, the square of that. So, and with 3, same case, you get again the square of the scale factor, but basically with the index of 3. So you can rewrite this matrix as H1 squared, H2 squared, and H3 squared. As a fun little exercise, I have a challenge for you. In part 1 of our journey to relativity, we basically found the metric for the cylindrical polar coordinate system. Now, having the techniques that you learned like right now about finding the natural basis and such, try to use that to find basically the metric of the cylindrical polar coordinate, but now in that fashion. I'm not going to do it fully right here, but I am going to give you basically the basic gist of what you need to do. So in essence, the first thing you need to do is you need to find the position factor for an object described in terms of the cylindrical polar coordinates. So in essence, what you need to do is you'll have x1 times e1 hat plus you need to, in essence, plug in their components, basically the Cartesian components of these cylindrical polar coordinates. So if you remember, x1 was rho cosine of phi, x2 was rho sine of phi, and x3 was just equal to the z-axis. So if you plug these in, you can then find the directional, you can then find the displacement factor, which would just be the derivative of this. And if you have that, you can find the magnitude of that displacement vector, which should then give you the metric. And if you wanted to check with what we previously did in the Journey to Relativity Part 1, you can square the answer you found right here for the magnitude of the displacement vector, so for the magnitude of the R. If you square this, you should in essence arrive at the metric for the cylindrical polar coordinates, and that should in essence give you the same value as the one which we got in our Journey to Relativity video part 1. Try it, see if you can come out of it, and if something goes wrong, there's a high chance that it just has to do with differentiation and nothing too tricky. Now finally, let's talk about the ultimate thing which we wanted to talk about, and that is describing vectors in terms of curvilinear coordinates. And that just basically means describing vectors in terms of, like, say, curved coordinates with curvature basically, and basically in terms of any coordinates, you could say. So for example, if we have a vector v, earlier we said that, okay, we can describe this in terms of its component times the Kronecker delta ij. Well, we can do something similar, but now instead of using the Kronecker delta, we can use the so-called metric tensor ij to, in essence, denote the same thing. We're describing the vector, but this time in terms of a generalized natural basis instead of specific, say, the Cartesian coordinate. We can do the same thing for another vector. We can say that its component is, say, uj, gij. For example, in this case, we chose the index of j for the vector instead of I, because, for example, if we wanted to find the dot product, what we can now see is that the dot product of v dot u it should, in essence, be the same thing as what we did earlier, but this time just with this metric tensor right here instead of the Kronecker delta. So we should get vi uj, so the components multiplied by each other, or instead of having their corresponding physical bases of ei dot ej hat, we'd have their corresponding natural basis of gi hat, gj hat, and we can remember that this was just basically the metric tensor. This being how we describe in essence the dot product of two vectors in terms of a generalized coordinate system, so in any curvilinear coordinates. Now, in the actual book of covariant physics, this is the point at which the author goes to show that, for example, what we did earlier in terms of describing the metric as, for example, or the square of the metric in terms of gij, dui, duj. Instead of using dui and duj, most literature just uses dxi and dxj, which might seem a little bit confusing as we typically associate xi, like x1, x2, x3, etc., with Cartesian coordinates, but it doesn't mean Cartesian coordinates from basically, it doesn't just mean Cartesian coordinates from here on out. Instead of if I basically just say that, okay, this means Cartesian. If I don't specifically mention that, okay, I'm talking about Cartesian coordinate system, you can assume this to be the xi and xj, you can assume it to be any generalized inputs that you can put for your coordinate system. So that's why at first we talked about ui and uj, because it was easier to see that distinction. But from here on now, it might sometimes be a little bit confusing, but I will try my best to point out that, okay, remember that we're talking about like generalized coordinates. And plus, a trick to keep in mind is if you see this metric tensor right here, then you can immediately sometimes create in your brain that we might be talking about like some generalized coordinate system. So from here on now, instead of dui and duj, we're going to just say dxi and dxj, just for consistency with other pieces of literature out there. In terms of lowering and raising indices, we can use this new thing we call the metric tensor to do the same thing as the Kronecker delta used to do, and that is, for example, if we have a vector vi, we can use this gij to, in essence, lower and change basically the index from an I to a j. That is completely fine and possible. Similarly, if, for example, we have a u with lower index of j, we can multiply it by this value right here, by this metric tensor, but this time with upper index of ij, and that basically just raises this j index and transforms it from a j to an I. So these are all two things which we can pretty much do very similarly with the Kronecker delta, but right now with this new notation of gij. Now that we have that, we might wonder, is there like a hybrid Kronecker delta situation that is similar to what we had, well, with the Kronecker delta, of course, but with gij? Not necessarily. Actually, instead of, for example, instead of doing this, interestingly, what we're going to do is when we have this hybrid situation, we're still just going to use the hybrid Kronecker delta. So you can still say that, for example, what happens, for example, if we have ui and we multiply it by gik, and what happens if we have that and multiply it then later by gkj. So kind of split it like we did with the hybrid Kronecker delta. Then what you would have, of course, is that this component right here, when you do this little bit of a contraction, you get that you lower the index of I to a k, and if you multiply it by this gkj, you would get uj still. essence, if we notice that if we have this little bit of contraction right here, and that is very similar to just a hyperchronicle delta, we arrive at something called the orthogonality condition. And by orthogonality condition, I mean that, for example, with vectors, you remember that if the indices are the same, then you have a non-zero value. And when the indices are not the same, then you have a zero value. Now, from this given scenario, you can notice that if we, for example, were to interpret this multiplication right here as a matrix multiplication of, say, GIK with GKJ, we can then notice that this, in essence, should be an identity matrix, because at the end, it gets ui in here and it spits out uj. And the only way in which, again, you can, for example, in the case of orthogonal, because of the orthogonality principle, the only case in which you can have a non-zero solution is when I equals to j. So in that spirit, we know that these two objects should be the same. So something that gets an object into it and spits out the same object, or after matrix multiplication, that should be an identity matrix. This tells us, for example, that if we have Jij and we have the Jij with an upper index instead of a lower index, this should be the inverse matrix of this Gij, if we were to, again, interpret it in terms of matrix. Because it's only when you multiply, well, an inverse matrix by its original matrix that you spit out the identity matrix, basically. And that is why, in essence, people call the Gij with lower index the metric tensor, and Gij with the upper index in essence, the inverse metric tensor. And again, to finish this video off right here, we will talk more about tensors. We've been throwing that word around quite a bit, but before doing so, we will have to dedicate a full video to the topic and basically talking a little bit more about vectors, what they entail, and then slowly get into our definitions for what tensors really are. So right now, some of these things with Jij, for example, are quite hand-wavy, but the idea is that you understand how this particular term can be used for natural bases, which in essence are not dependent on, say, Cartesian coordinate system. You can use it for any curvilinear coordinate system. So I hope you enjoyed this video. I hope you enjoyed this journey to relativity, and I look forward to seeing you guys again in the next one. Cheers and bye.